All right, let me go get those from the copier. And we'll get the screens going. You guys want one of these? Fun for you. Here's gallery over here. All right, so let me get the last little bit of cables connected here, and then we'll be off to the races, as they say. Okay, so AirPods, need that. Hopefully they'll work. Where they disconnect and reconnect like every 2 minutes or something. It's very annoying. And if that would stop, that would be great. So, okay, so let's go to the Elgato, which means I've got it plugged into the wrong one. That one, okay. Okay, so there's one thing from last time I wanted to just revisit briefly, which was this special limit, which turns out that it's 1. And that may not be obvious. If you graph it, though, it's pretty good evidence that it ought to be 1. It is possible to prove that using a kind of clever argument that involves the squeeze theorem, but for our purposes, let's just take it on faith, okay, for now. But there was one problem that we didn't quite get to last time, so let's just say take on faith. Would be, how do you use that? So I think it was something like this. Was on the back of the last sheet. Yeah. Okay, so any ideas what to do? Can we just directly apply the thing I told you to take on faith? Not yet, right? What's the problem? Yeah, the 4, right? Sine of 4x and the x in the bottom, well, 4x and x are different things, okay? But what could I do to make it look sort of like the thing on the that we started with? I could multiply by a disguised form of 1, right? And then kind of be smart about kind of how I rewrite it. Yeah. Okay, now having done that, if x is going to 0, what is 4x doing? Also going to 0, right? So I could then say this part should go to 1, okay? Because if 4x is going to 0 and x is going to 0, then I might as well have sine of smiley face over smiley face, right? They're the same, they're going the same place, okay? So that part goes to 1, and then what do I have hanging on over there? I'd have a 4, okay? Right. So the whole thing would be 4, right? And of course we could graph that just to double check. So in fact, let's do that real quick. Let me open up Mathematica. And then plot, or over X, sorry. And then switch this to full screen. Okay, so if I graph this, and let me blow this up a little bit so it's easier for you guys to see. If I plot this from -1 to 1, then, which I just picked -1 to 1 because 0 is in the middle, and that's kind of where we're interested. 4 looks pretty good to me. What do you guys think? Yeah? Okay. So this is, of course, subject to the thing that I've told you that is 1, which again, so I just noticed I took the 4 out, so now it's just the thing I told you to take on faith. Well, 1 looks pretty good. Yeah, this is the trust me, I'm a doctor kind of part of class. Yeah, Owen. Uh, okay, that's an artifact of the graphing, right? So there should be a hole there. Like if I were to draw this graph by hand, I would have a little hole drawn at x equals 0. Um, but the way Mathematica graphs things, right, is it just picks a crap ton of points, puts them into the function to get the y value, and then is basically playing connect the dots. Um, and the resolution is such that we just couldn't see the hole. Now, if we zoom in on that point, by the way, though, so if I do something like this, right, then everything's good until we start to get like down to sort of limits of machine arithmetic precision, right? And then it'll start to kind of get, there's a point if we zoom any further, it gets all like crazy because it's basically just truncation errors left and right. So anyway, but yeah, it, I don't know why, there's probably a way to tell it like, hey, put a hole here or something. I mean, I know I've done it for, to construct graphs like that are on the top of the news sheet that has the holes and dots and stuff, but it's kind of, you have to kind of do it manual and it's sort of a pain in the butt. Anyway, so yes, but to be clear, right, the function is not defined at 0, even though the graph may mislead us to think it is. The but the limit is still 1, right? Because remember, the limit of the function and the value of the function have essentially nothing to do with each other. Okay, good. So let me go back to the Elgato. So we're going to talk about one-sided limits today, right? And so let's take this sort of picture that's on the sheet there, which I won't try and sketch. Well, I'll just do a crude sketch. So it's like, something like that. Okay. So where are the points that are going to be of interest? Well, let's look at, say, x equals 3. Okay, which let me label some axes here. Okay, so we've got 2, 3, 4, 5, 6 along the x-axis. Okay, so let's take x equals 3. Now, if I come at 3 from the left-hand side, oh, and I should probably sketch the y-axis also. So we've got 0, 1, 2, 3, etc. Okay, 4, 5. Okay. If I come at this from the left, then what I'm doing is I'm thinking in my mind, right, okay, 2.5, 2.75, right, and I'm coming close. What y value am I approaching? It'd be whatever the y value of this dot is, right, which is what, according to the graph? 2, okay. Um, Subject, of course, to my crude art skills. So this is 2. Now, if we come at it from the other side, okay, then I'm thinking 3.5, 3.1, 3.01, 3.001, right? I'm coming at it from the right-hand side. And then what y value am I approaching? Right, I'm approaching the whole. What's the y value of the whole? 3 in this case. And so this limit is 3, not 2. Okay, now, first off, the notation. How do I know whether or not I'm approaching from the left or from the right? What told me that? Yeah, the plus or the minus. So minus from the left, plus from the right. Okay, which, and this is one thing that I have had students kind of grumble about, like, why is it, like, we're in positive territory, so why is there a minus sign? Okay, but we're associating minuses in the left-hand direction. Okay, that's just the notation. Sorry. Go back in time with the sports almanac, and that'll be on my list of things to change. Although, actually, if I'm going back in time with the sports almanac, like, who cares, right? Just make a bunch of money and throw it in a bank, and then come back through my time machine, and then just kind of chill, right? Won't have to be teaching calculus if I've made a bunch of money from my time travel operation, right? Well, that's true too, right? um, yeah, if the physics department actually comes up with a working time machine, somehow I don't think there'll be physicists teaching at Wabash College much anymore. Yeah, although who knows what the future holds? But let me tell you guys a little story. So this is story time with Dr. McKinney. Let me get my book out. So one of the classes that I've taught a couple times now, and preview, I'm hoping to teach it again in the spring next year, is a course on spherical trigonometry and celestial navigation. Okay, so spherical trigonometry is the math that's behind how you navigate using the stars, right? And it's spherical because, well, I got news for you. What do we live on? A disk with the ice all the way around the rim, right? Yeah, we live on a flat world, flat Earth society. Um, so, touche, right? Yeah, we live on basically a giant sphere, and it's not perfectly spherical. It does kind of bulge a little bit at the equator end. So the radius of the Earth at the equator and the radius of the Earth, if you measure it this way, are not quite the same. And that's because the Earth is rotating, right? Um, okay, anyway, it's basically a sphere. And if you look at the night sky, I mean, we know that the stars are not the ancients thought that there was a giant, basically glass sphere surrounding the Earth, and all the stars were basically like painted on the inside of it, and it was this giant thing, right? Giant sphere. Well, now we know it's not actually like that, but it sure looks like that. And over the time scales that we humans live, it might as well just be that they're all painted on a giant glass sphere, okay, for earthbound purposes. So this was pretty late in the semester, and we were talking about how you can determine your position at sea if all you have is an almanac, a nautical almanac, not a sports almanac, a sextant, and a slide rule or something to help you do some of the calculations. And um, uh, the example I was working, I said, well, you need to pick a star that's at least 15 or so degrees above the horizon, because when you get close to the horizon, you have to take into account atmospheric refraction. And I said, now, if we were on the moon, we wouldn't have to worry about that because there's no atmosphere on the moon. You guys heard the one about the bar on the moon, bar and grill, great food, no atmosphere. Anyway, so I was just sort of casually joking, like, yeah, if we were on the moon or something, right? Like, and then one guy was like, immersion trip to the moon. And we all had a good laugh out of that. And then it kind of hit me, you know, in 100 years, that might not actually be out of the realm of possibility to take an immersion trip to the freaking moon, right? Or maybe it's 200 years, but like that really could happen. And then we had like real deep moments. It was real deep feels. Um, Peppy the Frog, like feels good, man, kind of moments. Yeah, it was really deep. Anyway, okay. So why did I bring that up? Time travel, right, right, of course. Okay, now you guys see how my brain works or doesn't, right? Okay, so um, what's the whole point of this? Well, what we're going to use this to do, and that we'll talk about this a little more next time also, is to build really our definition of continuity. So what we say is that the limit as x approaches some number a if the left-hand limit and the right-hand limit both need to exist, and they both also need to be the same thing. Okay, so that's really two requirements. And if so, then the limit that where the a, notice, doesn't have a little minus or a little plus, so what that means is sort of from both sides simultaneously, I guess, um, is that thing. Okay. All right. So is that cool? All right. Now, how many of you guys think that I can't spell? Yeah. Okay. IFF is lazy mathematician shorthand for if and only if. Okay.
Still think you can't spell.
You still think I can't spell? Well, you would be correct, because there are some words in the English language that I will never be able to spell correctly. They are Tuesday and guarantee. Okay, I always screw those up. And it's a good thing that we have autocorrect now, because, um, yeah. Yeah, those two are probably the ones I screw up most routinely. And Tuesday I have to use pretty often, right? Guarantee, like, I mean, fortunately, I'm not the CEO at Men's Warehouse. Otherwise, I'd have to find a new job, right? I guarantee it. You guys, actually, they fired him, so whatever. Anyway, okay. So, yeah, it is sort of funny, and that we start with these kind of limits, and then we talk about the one-sided ones. Like, wouldn't it actually make more sense to do it the other way? Talk about the one-sided ones and then the regular ones. I don't know, right? But c'est la vie. Oh, and the power is not powering. There's something wrong with this power outlet. It's one of these tamper-resistant ones, and it's kind of loose. And the power thing just does not like to. See, damn it, come on. There. It's got tamper resistant, so there's like a little plastic thing, and you have to put both prongs in at the same time. Otherwise, it like won't let you plug it in. If you guys have kids, you'll learn all about that, right? To keep them from electrocuting themselves. Although, how many of you guys actually electrocuted yourself with an outlet when you were a child? Uh huh. Natural selection, yeah. And what did it teach you? Huh? Oh, so you were like taking a hit every. Yeah. No, I can even tell you exactly which outlet I did it on. It was in my grandparents' house, my mom's parents, the particular outlet that did it. And many, many years later, this is maybe 2 or 3 years ago, I was there visiting and sleeping in that room and plugging my phone into that outlet. And it was like really loose, so the phone charger kept falling out. So my dad and I were changing it, and when he was, getting it out of the housing, it shocked him. Now he had on gloves, right? And he's like, "Damn!" I'm like, "Well, that's the same outlet that taught me not to play with electricity." So yeah. Uh, excuse me. Okay, so left-handed and right-handed limits both have to be the same thing for the limit to exist and be that value. Okay, now looking at the graph, what other things do we have that might be issues? Okay, so where's the other sort of problem point here? X value. Right, okay, so x equals 5 is our other problem child. Okay, now x equals 5 is interesting because what's the limit from the left? I'm sorry? Y 0. I'm sorry, I can't hear you. Oh, you mean the whole? It'd be 3. Okay, so what is the limit asking? As the x value approaches something, what are the y values approaching? Okay, are we good with that? So the answer to a limit is always a y value, if anything. Okay, so if we are approaching x equals 5, right, not y equals 5, what are the y values approaching? Let me scroll back up here. So I'm coming at it this way along this little squiggle. What are my y values approaching as I get closer and closer to x equals 5? Be the y value of that whole? Yeah? What is the y value of that whole? 3. Okay. If I came at it from the right, what would the y value be? 5. Okay. What's the value of f of 5? Actually, it does. It's 4 because that's where the dot is. Okay, so do we see the distinction here? The dot is the value of the function, which may or may not be the value of the limit. Okay, so here, the left-hand limit and the right-hand limit are different, and they're also different from the value of the function. Okay, that can totally happen, as it just did. Okay, so if the left-hand limit and the right-hand limit are different, what do we say about the limit? It does not exist because what is required for a limit to exist at a point? Yeah, the left-hand side and the right-hand side have to both agree and be the same value. And that did not happen over there at x equals 5. Okay, Gucci? Question, preguntas, fragen? 9? You have 9 questions? All right. Yeah, one of these days, Owen, I'll learn German and then I can actually like joke around with you. But yeah, what and actually on the subject, what languages has everybody been studying? All right, so German, raise your hand. Okay. Spanish. Okay. French. Are you in it now? No. Okay. Uh, Latin. Right. Yeah. Greek. No. Chinese. Something else. All right. Anyway, just curious. All right. So let's tournez-vous la page. Um, okay. So this one's kind of a weird looking function. Okay. Um, and looking at this thing, um, most of the limits are going to work out like they did on the last page. Okay. I won't even try to draw this one. So, first off, where are the potential problem x values that we would need to consider? What's going on at? So, what's our list of problem children? X equals 0, 2, 4, and also and 5. Okay. So, does that make sense that those are all problem children? Now, 2, 4, 5 are all problem children just like they were on the previous example. Okay, there are holes and dots and stuff like that. But what's going on at x equals 0 is kind of a funny story. So let me switch back over to Mathematica and let me graph this. Okay, or something that does has this property. Okay, so here is an example of a function that has this weird squiggly business. Okay, and one way to think about it is that the as x goes to 0, what is 1 over x going to do? Right. So what happens when you divide by smaller and smaller numbers? All right, let me rephrase the question. What's 1 divided by 2? 0.5. What's 1 divided by 0.2? All right. Okay. So it's bigger, right? Smaller denominator means bigger fraction. Um, and you know that 9 out of 7 Americans struggle with fractions. Yeah. Actually, that joke is only partly funny and partly realistic. I think this is in the 80s. So what's McDonald's most famous two hamburgers? The quarter pounder and then maybe also say the Big Mac. Okay, but let's take the quarter pounder. So the A&W root beer company, which also has a chain of fast food joints, right, decided, okay, we're going to introduce a third pound hamburger to compete with McDonald's. And what do you guys think happened? It didn't sell well because people thought that a third pound hamburger was smaller than a fourth pound hamburger because Americans are stupid. So, yeah, fractions are hard. Anyway, um, right. So, what's happening with this sine curve, right, is that as x goes to 0, 1 over x is getting to be larger and larger values. Now, what does sine of x do as you go off to infinity? Just plain old sine of x, right? It's just doing that up and down thing, you know, the sine wave, okay? Well, what's happening is essentially that the oscillations of the sine wave are getting compressed, and they get more compressed the further you get closer you get to 0, right? So this is why, like, you know, not very squiggly, getting more squiggly, getting even more squiggly, getting even more squiggly. Okay, so the question is, what's the limit of this thing as x approaches 0? Yes. Huh? Well, is there a closest value to 0? No. Okay. So the limit as x approaches 0, this thing does not exist. Okay, now that may feel a little weird, but here's why. What does it mean for a limit to exist? The y values have to be approaching a single number. But in a sense, here, we might think that they're approaching every single number between -1 and 1, because the squiggles are getting so fast, how are we supposed to tell? Okay, and so that's that's not a very precise reason, but it's good enough for Math 111. Let's put it that way. Okay, so is that kind of okay? Now, this, I will have to admit, is a very pathological function, right? This thing is a screwball. And if you were to ask somebody like Dr. Brown, does this thing count as a function, he might laugh you out the door, right? Because physicists, they have different rules than we do. But anyway, he would say this is a function that never actually exists in the real world. We never run into something weird like that, and you mathematicians just make it up to be jerk faces. Uh, and to some extent, he's not wrong, but yeah, anyway. Okay, so let's continue. So there, we've got 6 limits on there. So let's just double check that we've got all of these correct. We've already talked about the limit as x goes to 0 from the right, so the dude at the very bottom. But let's do the other 5, okay? So let me just pick one of them at random, other than number 6, and I'll pick on victims here in a moment. Okay, and see what you guys get. So we'll do a little bit more active learning here. All right, so when you're finished with all 5 of them, put your hand on your head. Or actually, you know what? I know what we should do. Oh, they're already here. I'll explain what these are in a minute. We're not gonna like have a keg party with our red Solo cups. Right? You know the song, Red Solo Cup. No cups for you. Okay, so what's the purpose of the cups? Red cup is, I'm stuck, please help. Green cup is, I'm finished. Yellow cup is, I'm doing fine, I'm working, leave me alone. But I'm not done yet. Okay? So you put the appropriately colored cup on top, and then I know how everybody's doing. Okay, so green cup means you're finished, yellow cup means you're still working, and you want me to leave you alone. Red cup means you have a question and you need help. Oh, look, a red cup. Perfect. We'll get you guys trained. Is this weekend the Super Bowl?
Yeah.
Okay. It's also going to be very, very cold, so watching the game is probably a very good thing for you guys to be doing. All right. Looks like we got a full slate of green cups. So, Mr. Galandak, would you please, what is number one? Limit as x goes to 4 from the left of our dear function f. 3. 4 from the left is 3. What's the peanut gallery think? Points for Mr. Galandak? Yeah? All right. Mr. Burns, number 2. 4.5. Peanut gallery says? Gucci? All right, Mr. Runge, number 3. Does not exist. Why? That's correct, but why? Okay, so the limit from the right is different from the limit from the left. How did you know that? Well, that was the first 2 questions, right? So the first 2 answers were different, and therefore answer number 3 had to be does not exist. Okay. In fact, we could have answered number 3 without having the graph if we just knew number 1 and 2 were correct. Okay. All right. Let's see. Now, what is your last name actually? Is it Near? Okay, so it's the backwards by American standards order. No, okay, I got it. Okay, Mr. Near. Why don't you do number 4? 2.2. Peanut Gallery says. Yeah, good. Mr. Silas, how about number 5? All right, why not? Why does the limit as x goes to 2 not exist? Yeah. So what's the limit from the left as x approaches 2? 1, okay, because that's the y value of the dot. What's the limit from the right? 3, and they're not the same thing. Okay, good. All right, so I think you guys have this pretty down. All right, so for the last little chunk of time here, let's do, quote, wacky limits. Okay, so here we have 2 functions, and they're both pretty wacky, all right? But we're not just interested in what the limit of f or the limit of g is, but combinations of the 2, right? So notice what we've got. Like number 1 there is the sum. Number 2 is the quotient. Number 3 is the sum, but at a different point, right? So different combinations of the functions. So why don't you guys take put back in your yellow cups? Okay. Now in red on the sheet, you see what the answer is supposed to be. All right. So what I want you guys to do is to reason through it to make sure that you see why the answer is what it's supposed to be. Okay. So does that kind of make sense? Yeah. Gucci? Yeah. All right. We should probably talk a little bit about Sunday.
Yeah.
So, and maybe mention it to these guys kind of right before they skedaddle. which the other thing I need to show you is sort of how to use Canvas as since you're in instructor mode, basically, you have different abilities than you would in, yeah, so like you can make announcements. It's not rocket science, but oh, good. And so you can see all of the, yeah, okay. Now, the one thing I think in Infinity, you probably can see the grades. Yep, I think so, because there's no way you're either an instructor or you're a student. There's no in between on there. So that means we get to have a chat about Ferpa. Uh, right. Basically, that's confidential information, right? It's pretty straightforward. Uh, I kind of think of Ferpa as like the professor version of HIPAA, which is the healthcare thing, right? Like, or lawyer-client confidentiality, right? If you're going to confess to murder, confess it to your lawyer, because he can't tell anybody. All right, so let's kind of pause for a moment and take a look at the first one just to make sure we're kind of all on the same page. So the first one asked us, limit as x goes to 0 of f of x plus g of x. Okay, the answer claimed is that it's 0. All right, now what do I have to do to verify that this is correct? What is the limit of a sum of two functions? Plus the limit of the other function, right? So what I need to double check first is what is the limit of f as we approach 0, and what is the limit of g as we approach 0? And then we'll worry about adding them together, okay? All right, now, what is happening to both of these functions as x approaches 0? What happens to f? Goes to 2. And what about g? -2. Okay, so this would be the limit as x goes to 0 of f plus the limit as x goes to 0 of g, which would be 2 plus -2. Last time I checked, that's 0. Okay, does that make sense? Right, so what are we doing here? What are we combining? We're combining, well, maybe not for this particular part, but for the next ones, right? We're combining our idea of one-sided limits that we talked about, that we've been talking about today, along with the business of the limit laws that we talked about last time and the time before. Okay, so does that kind of make sense? Yeah? All right, so continue A, and let's maybe talk number 2. Has everybody got number 2 at least figured out? So I'm not going to interrupt you to come back for number 2. Gucci, Prada? Yeah? Okay, let's talk number 2. Because what's going to be potentially funky with number 2? Like what's our spidey sense tingling about? Yeah, divide by 0 kind of problem, right? So we got a quotient, might have a 0 in the bottom. Danger, Will Robinson. Okay, we better figure out do we have that problem? Okay, so what is the limit as x goes to 2 from the left of the quotient? This is equal to what? It's the limit of the top divided by the limit of the bottom, assuming what? right, that the limit of the bottom is not 0 and that the limit of the top actually also works out fine and that we don't have a 0 over 0 problem. Okay, so the question is, do we? What's the limit from the left of each function individually? Oh, you're right. Yeah, sorry. Okay. All right, so what's f doing as x approaches 2 from the left? Goes to 1, was it? Agreement? Disagreement? Yeah? Okay, what about g? You guys agree? Okay, so what's the limit of the quotient in this case? It'd be 0 divided by 1, which is 0. Okay, so this is why actually it was important that g was on top, because otherwise we would have had an issue. Okay, okay, so does that sort of make sense? Limit laws plus one-sided stuff? We? Okay. All right, so we got just a couple minutes left. Let's talk about SI. It's been a few minutes since we've talked about that. And Champ is here. Champ, you want to give him a spiel? Yeah, we'll add all that to Canvas so you guys can see it. It's pretty easy. Which that actually reminds me, what time Sunday is your session? What time is the Super Bowl? So will it be over by 8:30? This might be a problem. Yeah, okay, we'll figure something out because somehow I think that the Super Bowl is gonna. I don't know. How would you guys would rather do math study than watch football? Really? Yeah. Okay. All right. Anyway, we'll post all that info to Canvas. But yeah, it's not mandatory. All right. So what's the difference between the QSC and SI? They're both students, right? Okay. Yeah. So SI is peer-led group study. Okay. QSC is, hey, I'm stuck on number 7 of this homework. Okay. They're both useful, right? Because you might be shocked to find this out, studying concepts and going over your notes and kind of things like that turn out to be helpful to do before you actually sit down to do the homework. Shock. Okay. Um, the other thing is that SI, it'll lag a little bit behind course material, and Sunday, the very first thing he's going to do is some work on those prerequisites, so the algebra, the trig, the things like that, so that I handed back last time. Okay, so if you got a not yet on something, right, you either got a pass or a not yet on a page. The not yet things that means we still got some work to do. Okay. All right, good. All right, well, have an excellent weekend. Please bring your cups back up. And question? Sure. Let me kill the stream real quick.